transform, then I will go to the next chapter. And these are the homework problems which we have to complete. So let's do one problem from this problem set. Let's do this one. B dash 2 dash 14 A. Suppose if you have a function, this is f1s. It's very blurry, but it is f1s. It doesn't matter whether you write f1s or this is the Laplace transform domain. S means Laplace transform, or this is the Laplace transform domain, which S is also like a frequency. Um, okay, now let's see. In order to find out the inverse Laplace, that is a question. In order to find inverse Laplace transform, you have to use the partial fraction expansion technique. So let me show you. If you have square, so you would start from the first coefficient as starting from the square, and then second coefficient which is less than a square, which is s. So now the denominator is from this left hand side, you will multiply the whole equation by s square. So multiply the whole both sides by s square. So you're left with 6s plus 3 equals to a1 plus a2 times s. So now you compare the coefficients. If you compare the coefficients on both sides, coefficient of I would say coefficients of compare coefficients of s term on both sides. So let's start from the biggest degree, which is s. So s, so we get what? Left side, the coefficient of s is left side is 6. On the right hand side, this is a2. So it means a2 equals to 6. So we found one partial fraction coefficient. Let's find out other. S power 0 means constant. So left hand side, the constant is 3. Agreed? So I found both the coefficients A1 and A2. Now let's plug it in over here into our equation number 1. So f of s, f1 of s equals to a1. Now it is 3 over s square. A2 is equal to 6 over s. Now you have to look at the partial the transform table. So if I go back to the Laplace transform table to compare what is the closest answer for our inverse Laplace. So let me show you. So if you take a look here, so I'm finding this 1 over s square. If you take the Laplace inverse, this is the time domain, this is t. So taking the Laplace inverse on both sides, so this becomes f of t. Inverse means like you go from frequency to the time domain, and I can write down this as 3t. And for this one, if you look closely, this is 1 over s, which is the unit step. So this means that 6 a unit step starting at location t. So this is your answer. Do you understand that?
With the instead
Yeah, the question asked by this gentleman, Professor, if we don't put one time t, it's still okay. But you know what happens sometimes? I tell you, 6 times 1 t minus t0. That tells me that it is delayed function like t0, which is so. But if it is written like this, it means right starting at the origin, the step value goes from 0 to 6. This is what it means. It's a good practice, but if we don't put this at 1 starting at time t equals 0, it is still considered understood that it is the step value starting at 0 time. Okay, so let's do one more problem. Problem number 2-16. When you see that the degrees of the polynomials are the same, then you have to think about it. You can do the long division. Make sure that the degree of s in numerator should be always less than the degree of s in the denominator. Then you can apply the partial fraction expansion. So in this case, I would do the long division. So I can write down 1 plus 2s plus 4 over s squared. Agreed. So what I can do here, look, can I write down, this is my f of s written in, after the long division, I can write down this like this. So 1 plus, can I write down 2s over s squared? Can I split this up? So the way I can cancel this out, so I'm left with 2 over s plus 4 over s squared. So now again, this is the complete uh, Laplace transform form. So now you can easily take the inverse Laplace transform of each term individually. So let's take the inverse left hand side. It becomes f of t. What is the Laplace transform of a unit? Look, if you take a closer look, it's a little blurry, but if you take a closer look, if you have a unit or one, inverse Laplace is delta function, which is an impulse of magnitude 1. So what I can do here, I can write down delta t. Delta means impulse. How about this? This is again 1 over s. The Laplace transform, inverse Laplace of 1 is 1. Agreed? So 2 times 1, I don't need to write down. But for a good practice, I will write down it is starting at t equals to 0. And for this one, I can write down. So you see my point? This is your answer. So if I draw um, if I draw these functions on the t domain, so at 0 we have a straight impulse of magnitude 1 and the step value of, I would say, let's make it 1 here and 2 here, because and then 4 times t. You don't have to plot it. I'm just showing you how it looks like. But anyways, let's do one more problem. Have you understood this problem? Can you guys hear me? The online students, please type in yes in the chat box if the technology is working. If
It's
no,
working.
I'll. Oh, thank you. Students are hearing in the online. Um, okay, let's do the next question. I'm gonna I'm gonna show you the solution of question number 17. It is little blurry, but let me write it down here again. Obtain the inverse Laplace transform of this function. The good practice is I will always start doing the factorization. Can I factorize as a discrete, what we call discrete roots? So let's do this. -2 plus minus b square minus 40 over 2. Agreed. So I don't see this is not a real root. It is a combination of complex roots. So I can write out -1 plus minus 6 iota. Do you agree with your professor? I'm sorry, this should be 3 because the 2 has divided by on both sides, so I can write out, right? This is the root number. So in this case, when you see the complex roots, then how would you solve this question? Let me show you. The way you will solve this question, so f of s equals to s over s square plus 2s plus 10. Let's write down, let's write down the partial fraction coefficient over here. So when you see the degree is 2 in the denominator, so what you have to do here, you have to write down as plus b. 1 degree less than the degree in the denominator, s square plus 2s plus 10. So I can write down this as a factor, two factors of these roots. Look, can I write down these two? If I bring this on the other side, can I write down? Can I write down like this s1 square plus 3 square? How did I write it down? Look, I if you multiply like s plus 1 plus 3 iota, what is this? One root is this s plus 1 minus 3 iota. Agreed? So I just wrote down these two factors like this. And now imagine this is A, this is A, this is B, this is B. So you remember the formula A plus B into A minus B. What is that? A square minus B square. Agreed? So can I write down S plus 1 whole square minus B square? Can I write down like this? Yes. So now S plus 1 whole square minus, and this minus iota square equals to minus 1. Minus minus becomes plus. So can I write down? So the way I wrote down this, it comes from a square minus b square when you multiply these two roots together. Do you understand this? It is going to help me to solve the question. Look, how is it going to help me? Look over here. S plus 1 whole square plus 3. The same thing in terms of two roots being multiplied together. I just split up into and plus b separately. I'm sorry, I forgot to write down 2 here. Now, guys, how will you find out? So let's do one thing. Let's do one thing here. I'm gonna show you. Let's find out the partial fraction coefficients here. Then I'll come back to this equation for the moment. I will solve this later. Let's do this. S over s square plus 2s plus 10. So can you tell me if you multiply both sides by the denominator of the f of left hand side? Can I write down like this? Now, the way I did, I multiply both sides by the denominator of the left hand side. So this is cancelled. Okay. So now compare the coefficients. Comparing coefficients of s. So s highest degree, left hand side the coefficient is 1, right hand side coefficient is a. So this is my first answer. Left hand side, the constants, there is no constant on the left hand side, it is 0. There is one constant on the right hand side, which is b, which is 0. So that means I'm gonna plug it in. Look at over here. I'm gonna bring this into my next step because I have found the values of the partial fraction coefficients. Agreed? So let me erase this line here. Now let's plug it in. This factor, this term goes to 0 because b is 0. The left hand side, a becomes 1. So let's figure it out. S plus 1 whole square plus 3 square. And now you remember, if you go to the Laplace transform table, yes, it is not visible here. Maybe I want to show you this one. Maybe I just explained it last week. Maybe I did that. This was the last week lecture. Yes. If you take a look here. Now I'm gonna paste the formula for exponent. So look, sine. I need this s in the numerator. So will this form work, or the down first form? What do you suggest, your professor? Which is the closest answer? Because I want to go back to this form. So I believe this is S. This is S. Am I having S? Can I bring S plus, like, can I bring S plus 1 here? Let's do 1 plus 1 minus 1. Can I do right like this? By adding and subtracting 1, I'm not gonna change the whole question. So, but it's gonna benefit me. Look, how is it gonna benefit me? Look at this. It is the complete form of this form. Agreed? So negative 1 over s plus 1 whole square plus 3 square. So now if you take the inverse Laplace of this term and inverse Laplace of this term, this is, what is this equal to? So can I write down like e to the negative t cosine 3t? This answer? Do you agree with your professor? And how about this one? This term is 1, but here it is omega. How should I bring 3 in the numerator? What I will do, look, I will multiply by 3 divided by 3 on in the numerator and denominator, so that it will not distort the question. So now, so look, 1 over 3 is for this 3. Okay, this 3, but this one is exactly what we have on this side. So I can write down the inverse Laplace of this term like this: negative t sine 3t. So this is how you complete the question. This is exactly what is requested in the question. Find out the Laplace transform of this f of s. So have you understood this question? Now the way you will solve, look what it means. If you plot it, the cosine 3t sine 3t. So it's a wave, combination of wave. So maybe it's like this wave, it's pure sine wave. But e to the negative t means it is going to be expressed, and a time will come this wave becomes 0. So that's why you then when the roots are in the left hand side plane of the Laplace plane, means real axis, imaginary axis, then our roots are lying negative 1 and 3 iota and negative 3 iota. So these are the two conjugates. They always like in a pair form, like complex conjugates. So in this case, the what we call the times response function, it looks like this. It will become to 0 after a certain time because of e to the negative t. If you see e to the positive t, then what will happen? this will grow and unbalanced. We call this an unstable system. When you see a positive t, we must have to have a negative in the exponent in order to express the sine and cosine signal. Do you understand this question? Let's do one more problem. I'm solving some of the homework problems just to explain that how will you solve it at home. I'm fine with this. You can just rewrite the solution by yourself. Okay, rather than copying pasting, I would suggest you try to understand the lecture and try to do it by yourself so that you should learn over here. And let's solve one more problem here. Problem number 22. Let's solve problem number. The question states this is a differential equation, the second order differential equation. Problem number B dash 2 dash 22. So the question is x double dot plus 4x equals, and the initial conditions are given 5 and the initial velocity equals to 0. And make sure that the Laplace transform of second order derivative is equal to s square x of s minus s x of 0 minus x dot 0. So this is the Laplace transform. We just did that last time. If you see, I'm going to show you. Did I show you this one? Maybe I explained in my lecture if I remember. Okay, uh, but it is for sure that Laplace transform for yeah, in this table, maybe in this table. But anyways, this is the Laplace transform of the. And how do you write down the Laplace transform of the first order or the first derivative? S of x minus x of 0. And Laplace transform of a variable without any derivative is big letter S. Usually the notation is the big letter for the Laplace domain, small letter for the time domain. So let's use this equation. I'm going to use this fact and apply it over here. Can you take the Laplace transform on both sides? So s square x of s minus s x of 0, which is 5. Look, x of 0 is 5. X dot of 0 is 0. So I'm going to write down 0 just for your help. Just where am I writing this down? And 4x, small x is big X, correct? And the right hand side is 0. So now what is the next step? So we have to find out x of s. So take x of s common, s square plus 4 minus or 5s on the right hand side. Agreed? So then take x of s only on the left hand side. So I'm dividing by the s square plus 4 on both sides. So this is my sorry, 5s. So now it is very close to the Laplace transform table. Let me bring this table to you in front of you and you will help me which row is best row to solve for the inverse Laplace transform. So what do you suggest me? Row number 10 or 11? Which one do you suggest your professor is very close to our inverse Laplace transform? 10 or 11? Please type in the chat box. Um, I think students are still needing some. So I will say row number 11. Do you agree with your professor? So let's do this. Inverse Laplace of the left hand side is becomes x of t. The right hand side is 5 is outside, s over s square 4. What I'm gonna write down, look at this formula. So s square, so s square 4. So I can write down cosine 2t. You agree with me? So this is the solution of this second order differential equation. Have you understood this question? Please type in yes in the chat box if you understood this question. Khan says yes, Christian says yes. Okay, that's good. Thank you guys. So let's do the next question. One more question, then I will go to the next chapter. So let's do one more problem. Let's do the last problem of this chapter problem. Let's do this one. B dash 2 dash 25. Caleb says yes. That's good. So I hope that you are understanding the how to solve the differential equation using the Laplace transform. So let's do this B dash 2 dash 25 question number. And the question is obtain the solution means like x of t, like inverse Laplace by using the differential equation, the Laplace transform. So x dot of 0, it is 0, x of 0, and luckily both initial conditions are 0. That's good that we don't have to a complex situation. So the first thing I would do, take the Laplace transform. So s square x of s minus 0 0, I don't worry about because both conditions are 0, so I don't need to worry about writing the remaining part of the. So how about the next one? The right hand side, the Laplace transform, look at here. Omega over s square plus omega square. It is the sine omega t. So if you compare, this is omega is 3. So I can write here 3 over s square plus 3 square, which is 9. So I can write down here like 9. So let's bring the x of s out, factor it out outside. So I can write here, look, I can write here like this, s square plus 1, s square plus 9. And then what I'm gonna do here, I will multiply. Oh, first of all, let's do the partial fraction expansion. You will help me because this is a square, so I need a polynomial with one less than the square. As plus b over s square plus 1 plus cs plus d over s square plus 9. That's how I will expand this with a summation sign. And that is the beauty because I can apply the Laplace inverse using each term separately. So now what I'm going to do, multiply on both sides by the denominator of the left hand side. So I can write down here 3 equals to as plus b times s square plus 9. Agreed? Plus cs plus d s square plus 1. Agreed? So now let's compare the coefficients. Can I write down one more thing? Let's write it down, as cube plus 9as plus bs square plus 9b. I'm just opening the parentheses to help myself. Cs cube plus cs plus ds square plus d to help myself to find out, comparing the coefficients. Now comparing the coefficients, s cube term, first of all, write it down. Left hand side, there is no coefficient of s cube term, so it is 0. Agreed? So the right hand side, I'm seeing two terms with the s cube coefficient. So I can write here a plus c. This is equation number 1. Let's assume this is equation number 1. S square, the coefficient. Left hand side, you don't see any coefficient of s square, so no term left hand. So right hand side is b plus d. Agreed? Left hand side, no s term. Right hand side, 9a plus c. Agreed? S of 0, constant term. Left hand side is 0, constant. And do we have 9 and d? So 9b plus d. So now we have 4 equations, 4 unknowns. Now it's a matter of linear algebra, which you have studied many times. So can I write down? This is d, by the way. It's not b. This is d. So let's do some math here. So I can take equation number 1 here. 9a plus 9c equals to 0. And then equation number 3, this is equation number 1, and equation number 3, 9a plus c equals to 0. Negative, negative. So you're left with 8c equals to 0. C equals to 0. So the good thing is one coefficient is 0. It's little more simpler. So that means from A equals to 0. So A is also 0. So now look, A is also 0 and C is also 0. So what is B and D? So let me write down B and D. So let's plug it in over here. B and D, equation number 2 and 4. So if you do the math here, so B becomes equal to 3 by 8. I'm leaving this to you. When you go home, so do it by yourself, whether you get 3 by 8 or no. Okay? Will you work this week to complete this question? Practice this again, this homework problems. Please type in yes if you finish this homework this week. It's okay. So now let's do this. I'm gonna write it down here. This whole equation. Look over here. I'm gonna write this down again just to help you how it looks like. This is not included, so obviously this is not included. So let me write it down here. So negative is 3 over 8 over s squared plus 1. Agreed? Negative 3 over 8 over s squared plus 9. So now look over here. So 3 over 8 is outside. Now I'm taking the inverse Laplace from here. This is x of s. Taking inverse Laplace. 3 over 8 is outside. What is the inverse Laplace of this term? It is sine of t. And what is the inverse inverse Laplace of this term? It is negative 3 over 8 sine of 3t. This is your answer. Because look, because sine omega t equals to the Laplace transform. Sine omega t equals to omega over s square plus omega square. Do you understand the solution of this problem? Oh yeah.
Professor, I have a quick question.
Yeah, what is the question?
So for that second part where it's s squared plus 9, should we have to
Yeah,
divide?
you're right. I'm sorry. I should have written here. Let's do this. So what I should have written 3 over 3 again here. So to 3 over, is it correct? I'm sorry. What I'm doing here. So look. That was a good question. So can I write down like this? 1 over 8, 1 over 8 outside. Can I write down like this? 1 over 8. Do you agree with your professor? With that, we have finished this chapter number 5 coming from a different book. It's just a review of the Laplace transform. So let's do chapter number 2. You remember we left chapter number 2 earlier. So now we are going to start that chapter number 2 and see how it goes. It's more of the dynamics portion. Okay. Okay, let's start here. Rigid body motion. So a rigid body performs three major types of motions. So let me go over here, cut and paste some of the topics here, which will be helpful for you. When you go home, review this chapter, read it, and look at this picture. This picture is telling us that the rigid body can translate rectilinearly. We call this a rectilinear motion when these two lines are always parallel. And what are these two lines coming from? When you mark 2 points on a rigid body, for example, a football, and when you mark and you throw it, if it goes straight, the parallel lines, then this is a rectilinear motion. But if it is a curve, the paths defined by the football on each for each point inside the football, if it is a curve path, it is a curvilinear translation. Both are translation. One is a rectilinear when the path is parallel, both lines, and when it is, if it is curved, then is the path is curved, then it's a curvilinear motion. And if it is fixed about one axis, fixed rotation, and if it is a combination, which is general plane one, when it is rotating, you see it is rotating as well as it is translating. So it's a combination of curvilinear translation plus the rotation about one axis. So it's a curvilinear motion. This piston is translating, which is rectilinear translation, and the connecting rod, one end of the connecting rod is attached with the crankshaft, which is pure rotation, but the other end is translating, so it's a curvilinear. I would say it is general plane motion. Let's do one problem. Consider the pendulum shown in this figure. Obtain the description of the velocity and acceleration of point G. This is a point G as a function of theta dot, and theta double dot in terms of normal tangential. This is normal unit vector. This is tangential unit vector. So we have to find out the velocity and the acceleration. So in terms of normal unit vector and tangential unit vector. So when I consider velocity r omega, R is considered as the radius or this arc length, which is L. In our case, this is L. Since the question states you should not use omega but use theta or theta dot. So omega equals to theta dot. Agreed? And this is the tangential velocity. Everybody knows that the tangential, when a path is ground path, then tangential is r omega. Agreed? So I can write down e to the, or e sub t is also the way, or you can write down l theta dot t unit vector. Both are correct. If you write down in the book notation says e sub t, so I accept both. It doesn't matter. Have you understood the answer? First answer. The next answer we have to find out the acceleration term. An acceleration term, tangential as well as normal. And a tangential, you will use this formula. Time derivative of velocity gives you the tangential. And this has already been, I would say, if you take a look, this is the acceleration of a centripetal acceleration is written as v square over r. R in our case is L. And the unit vector is normal unit vector, or e sub n, it doesn't matter. So this is tangential unit vector. Agreed? So now what is v? We already calculated v as L theta dot. So can I write down time derivative of L theta dot t unit vector? So now let's take the time derivative. L is outside because it's constant, so I can write down theta double dot. So this is the um, acceleration tangential component of the acceleration term. And how about the normal acceleration? So for the normal, I can write down here v equals to r omega. I know that r omega is L, r is L in our case, omega is theta dot, but it is square over L. I would say square r, because this is v square, so we have to take the square on both sides. This L is cancelled by this L, so you're left with L theta dot square. So the final answer for the acceleration with the vector form is, first of all, I write down the tangential unit vector component of the tangential vector. I can write down L theta double dot L theta dot square. Now the next, this is a complete answer for, we already wrote down the acceleration and the velocity in terms of normal and tangential unit vector. Agreed? Now let's do the next part. Says find out the, in terms of the same velocity, obtain the description of velocity and acceleration in terms of the rectangular coordinates x and y. Look, this is my x. What is x? If you closely take a look, this is my x. This is my y-axis. I'm just overwriting it to show you that it is visible in our sketch. So I'm gonna draw this sketch again. Can I write down like this? If you draw the motion has been written down in terms of x and y distance. So can I write down x in terms of polar coordinates and y in terms of polar coordinates? And v is vector form is x dot I unit vector and y dot. This is the formula, general formula. So what is x dot? So you have to take this expression and take the time derivative of this. So L is constant, so this is outside sine theta. Time derivative of sine theta is cosine theta. And again, you have to take the time derivative of the chain rule. Agreed? Similarly, y dot, take the time derivative of this I can write down here negative L sine theta times theta dot. So this is the complete answer. So you just have to write down I unit vector with this. So I don't need to rewrite everything. You can now for acceleration term, I want to write this down in terms of AXI, AY, J unit vector. And this is my x dot. So can I take the double derivative of this? So let's take another derivative of this on the left hand side. And now L is outside first function. This is a product rule of differentiation. Okay. I would say first function into the time derivative of second function, the second function time derivative of first function. So if I rewrite here L theta dot cosine theta minus L theta dot square. This is my acceleration AX. This is also acceleration AX or of the I unit. Right? Agreed? Have you understood this one? Now the next thing you have to take the time derivative of the y term again. Y dot, sorry. AY equals to y double dot. So negative L first function into the derivative of second function into the derivative of first function with the chain rule, because they are two different variables. That's why we have to apply the chain rule. So then this is the answer for this. So AY equals to negative L theta double dot sine theta negative L theta dot square. So this is my jth component. So that's how you complete this question. Have you understood this? Please type in yes in the chat box if you understood how we resolve this question in both A and B. Christian says yes. Khan says yes. Caleb says yes. And inside the classroom, she says yes. He says yes. Rob says yes. That's good. Let's do the next section. The next section is about the generalized coordinates. So any other than the normal tangential coordinates, you can define the motion of a mass. You can define a motion of an object completely defined by other coordinates. Like in this case, rather than x or y, it completely defines x and y. You can easily locate the location of the mass by giving the x position and the y position. But how about if we generalize coordinate? What are the generalized coordinates other than the reference coordinates? You just define the motion by a different coordinate, like over here. Can I, if I explain the theta, is the generalized coordinates here. So another example here. Now you see there are two masses, so we need two degrees of freedom or two generalized coordinates. So what you suggest me for this mass? Can you tell me which coordinate is very useful, which defines the motion of mass m1? X1. Good job. How about this mass m2? Can you tell me which coordinate you think is the best coordinate to define the motion? It's rotational. Okay, theta. Good job. You see, so we have found. So there are two coordinates. Similarly, I'm giving you another situation, and you will help your professor about the generalized coordinate. Okay, look at this picture, and now you will help me for the first pendulum. These are the two double pendulum situation. What is the complete definition? Which coordinates do you suggest me? Theta 1 and theta 2. So this one defines the first step pendulum position on the theta 2. And when you see two masses, when you see two, you need two generalized coordinates. Similarly, if you take a look here at this example, what two coordinates will completely define the motion of these two masses? Yes, x1 and x2. You see, she is right. So we have found the answer. So one more question, then I'll start the problem. Here is the another example of generalized coordinate or degree of freedom. We also call them a freedom, degree of freedom. Now you will help your professor. This roller is like a big drum or whatever is a roller. It is translating, like position is changing with the time, and it is rotating. So do you think it is defined by, I would say, either x or theta, because x and theta are related by this position. Now in this case it's a string, like string is both boundary conditions. Over here it is grounded, here is, now you just pluck this string and just leave it, so it moves like a wave. So there are infinite number of masses. So you will see in this case you need a infinite number of degrees of freedom. So we will study continuous system soon. Let's do one problem. In this case, pulleys can be used to change the direction of an applied force. Okay, to amplify the forces, in our example we will assume the cords, ropes, chains, cables that drive the pulley do so without slipping are inextensible. If not, then they must be modeled as springs. Okay, shows this figure shows this is the same figure which they are talking about. A simple pulley system. Suppose the pulley is free to rotate. This pulley you can easily move up and down and rotate, but not horizontally, just the vertical constraint. So vertical motion. So L is the defined as the length of the cable. So the length of the cable is L, the complete L, which is attached to support. Determine the relation between omega y dot x dot. So now I will say in the left hand side from figure A, look, this is L1. What is L equals to? L1 plus, this is R radius. So what is this semicircle? This semicircle is pi R. Agreed? Now about B, what is the total length of this cable? So look at this. This piece 1, and this piece 2, and this piece 3. Can you tell me? Look at this. Number 1, L1 minus y. Agreed? Second piece is what? Look at here. Can you guide me? What is second? So this is my x, this is my y coordinate, this is my x coordinate. So if suppose x is like 10, y is 5, 10 minus 5, that is the difference, correct? So can I write down x minus y, that section which is piece number 2, agreed? And this is section number, piece number, how about section number 3, third piece, which is pi r, agreed? So now this is equation number 1, this is equation number 2. So we know that y equals to, now y over here, r theta. Okay. So x equals to r theta. Agreed? This is this portion. So if this is r, this is theta. So let's do one thing. Compare equations 1 and 2. So L is both side, L is same, L1 plus pi r, L1 minus y plus x. Why am I writing double? So minus 2y plus x plus pi r. Agreed? This is cancelled by this, L1 is cancelled by this, so x equal to 2y. And if you take the derivative, x dot equals 2y dot. And you know that x equal to r theta, r theta dot. So left hand side r theta dot equals to, omega. Oh, r theta dot is also omega. So the question states, find the relationship omega y dot x dot. So we found some, that means omega equals to 2 over r y dot, and the relationship between x and y is x equals to 2y. That means that if the center of the pulley moves like 1 centimeter up, if the center of the pulley moves like 1 centimeter up, the this end moves 2 centimeter up. You see the what it means? So the center moves slowly as compared to the edges or the circumference of the pulley. Do you understand this question? Let's do one more problem. Consider the system shown in the figure 2.1-7. How many degrees of freedom does it have? So either x1 or x2, both. It is just one single degree because it's just one rope. You see, it's just one rope. And when one rope moves to the left 1 centimeter, other end of the pulley also defines the equation. So the degree of freedom x1 or x2, both are accurate. Determine the velocity x2 dot, acceleration x2 double dot of the mass m2 as a function of velocity, as a function of velocity, I'm sorry, function of acceleration here, as a function of x2 dot, as a function of, agreed? So now the way I will start this question, the length of the rope, I would always start from the length of the cable. So let's do this one piece. And look, this one and this one, they are both equal to x2. So it's a second piece and 2 times the second piece. You understanding? And then comes the third piece. So let's do this. Length of the cable equals to piece number 1, which is D, piece number 2, which is 2 times the x2, and piece number 3, which is x1. I'm ignoring the circumference. This half semicircle, I'm ignoring this because it remains constant. If you take the velocity, time derivative of this one, it goes away. So can I write down L minus D equals to 2x2 plus x1? So the D length does not change. If the pulley moves, if the mass moves to the left or right, the D length, it remains constant. So if you take the time derivative on both sides, how about this? So what will happen? The left hand side becomes 0, 2x2 dot plus x1 dot. Agreed? So, or I can just rewrite the x2 because our question was write down the velocity of x2 in terms of x1 dot. So I can rewrite here negative 1 half x1 dot. This is my first answer. And the second answer, you have to take this again, the time derivative of this function. The second answer. Some of the questions I have solved on YouTube, I'm going to share with you some of the links. So, but let me take a step. Have you understood this question? Right? Agreed. So the next thing is the kinetics part, that force equal to mass times acceleration, and the moments, summation of moments I times alpha or theta double dot, and the if you take the momentum, which is m linear moment mv, if you take the time derivative of mv, what is that? That is equal to ma, which is equal to force. So the if you take the time derivative of linear momentum, you get the force. Similarly, if you have angular momentum, which is defined as I times omega, this becomes I, v becomes omega. I means mass moment of inertia, I equals to ml square, or I would say if some the general equation is r square dm. Let me rewrite here. So this is mass moment of inertia. The unit of mass moment of inertia is kilogram meter square. So if you take the time derivative of angular momentum, what is this? Acceleration, angular acceleration. Okay, I alpha. So now this is also equal to, look over here, I can write down angular momentum. Now the thing is, I can write down time derivative I omega dot. And what is that? You know what is omega dot equals to? That is equal to sorry, I omega dot h dot equals to time derivative of mv, mv times r. You might be surprised, professor, what is this? So let me show you that the angular momentum can be written linear momentum times the moment arm. So linear momentum is mv, agreed, and the moment arm is r. So if you take the time derivative, what do you guys get for this one? dv over dt times r. So what is dv over dt? Is acceleration times r. What is mass times acceleration? Is the force. So if you take the time derivative of angular momentum, you get couple, or the moment. Sorry, not the couple, but the moment. Similarly, the way you did for the time derivative of the linear momentum, you get force. If you take the time derivative of the angular momentum, you get the moment. So I have made some videos on the YouTube. I'm going to share with you. And then one last thing before you leave, the parallel axis theorem. Parallel axis theorem. So if a body is not rotating about this center of gravity, but it's rotating about axis other than the center of gravity, then you have to consider the perpendicular distance between those two. Suppose it's d, and the actual rotation I sub o equals to I sub g plus m times d square. This is a angular momentum parallel axis theorem. You have to add another term which is mass times the distance between the uh, axis of the rotation. So with that, we have to understand that time is over. Thank you, guys.